Good morning, everyone. We are going to cover the part 2 for the classification material. Here are the outline for today. The material of today actually are quite heavy. Therefore, we might try to break the content into the two parts. At the very beginning, we are going to have the question QA. That come from some of the question come from the last week's 1 minute reflection. And then afterward, we will try to go over the performance evaluation again. Okay, some of the content actually being mentioned by certain students that they didn't understand. And then we also are going to talking about one very important concept called overfitting. Then afterward, the last week we're talking about decision tree, and some people already talk about the random forest. So today we're going to talking about some concept from the random forest. Then afterward, that is a very basic baseline for the machine learning method called Naïve Bayes and classifier. And then we will also try to go over some of the practice in the NTU Cool. And then afterward, we're going to cover the most attentive or like most watch, the very, very popular classification tool called neural networks. And then we will also talking about certain limitation if we could find. And then afterward, we are going to go over the convolutional neural network. We just try to cover a little bit about some of the concept and what are the possible limitation that the neural network actually has and can be somehow alleviated from by the CNN. And then afterward, we will also give you some of the practice or try to cover some of the fundamental the technique that's being popularly being used by the machine learning. Okay, so the next one. Here first, we try to go over some question from the last time. Okay, some students say that they feel confused, that they do not understand when we actually having, I hope you guys remember this figure. When we have that figure, you say, why we need to splitting into 9 to 1? Because we say that this 9 element in the C0 and 1 element in the C1, we consider that is better as compared to this 5, 5. Okay, we say last time, say this one is called homogeneous, and because they do not have too much randomness. And then this one, actually we say that is called non-homogeneous because they have a very high degree of impurity. Okay, first, maybe some student already see that is a 5 for C0, 5 for C1, so they thought that we split the element. The fact is we don't. This one, you can imagine the 5 actually is the correct answer. Okay, so for example, you can imagine we have 10 example. Okay, among 10 example, their correct answer is 5 for C0 and 5 for C1. And then these cases is also the same. We have 10 record based on their correct answer. 9 actually is marked as C0 and 1 is being marked as C1. Okay, so we did not split them. We just tried to talking about the distribution in our original population. In that cases, that so you can imagine we have 9 for these cases, 9 for C. I actually have a mistake right here. 9 for C0 and 1 for. So this one is not. I actually make a mistake. Okay, and I don't want to record again. So this one is 0 and this is 1. Okay, 9 for C0 and 1 for C1. And another cases is also 5 for C1 and 5 for C0. If you actually utilize entropy to calculate them, you will find out the entropy value for this case, 9-1 case, is 0.41. Remember, entropy 1 means very, very random. Entropy 0 means very homogeneous. So 0 is our goal when we try to do the classification in the decision tree. Okay, and then the 5 right here, if we calculate them, the entropy is 1. Okay, so you can actually see in these cases that the 9-1 actually is closer to 0 as compared to entropy equal to 1. So that is why last time when we actually asked you this question, say which one is better? And the answer will be this 9-1. Remember, we did not really split them. Okay, so then even though I already talking about what is the parallel attribute, but still have certain students say they don't really understand what it means. Maybe if you have the question is you do not take the data structure courses in the computer science, so some of the terminology that we mentioned might be quite new to you, okay? And then so they try to, so the reason we call them parent is because in computer science, we have a concept called tree. So for example, this is a tree, okay? And then last time, I don't really remember if I already say that. The first, this one we call them root. So the reason we call them tree is because if you try to reverse them, you will find out then all of them right here look like leaves of the tree. And then we having one node in the very in the bottom. So then right here is actually on the top. Actually, we call them root. Okay. Root, R-O-O-T, root. Okay, so then so if you actually right here, if you have this node called null, and then the upper node, it will be its parent. Okay, so then I probably, because I consider this one just so common for me, so we forgot to mention that this is a tree. I'm sorry for that. But then if you actually go through this one, let us try to utilize some other example. Okay, so then this tree, actually, you can imagine they might directly learn from our training data. Like our training data just look like this table. And today, if I actually have an attribute, or like we say, we have a branch node called tax income. And then what are the parent tree of, what are the parent node or parent attribute? Is you go upper, and then I try to find my browser. Okay, so then right here, you go upper, then you will find out this marriage status is a parent node. And then you can actually see in my table right here, we try to sort our data based on their marriage status. Okay, so in this marriage status right here, then sorry, so you probably see that the first, actually we follow the first attribute called refund yes or refund no. So you can imagine the top 1, 2, 3, this attribute, this record actually is being taken care right here. Okay, so the no part from the 4 to 10, actually those record, well, difficult. This record actually are the one that we suppose it should be managed with. Okay, so that's the first thing. Okay, but among those records, because you actually can see from these branches, okay, marriage status actually have 7 records, and then 4 of them are no. 4 of them actually are 3 of them are married. I try to change my browser, otherwise I have difficulty to see them. Okay, so 3 of them are married. So you can imagine those records will directly go to this part. Okay, this part, because they actually would know the marriage actually are no. And then these 4 will go to these branches. Hope that is clear. Okay, so then afterward, then you can imagine based on this 4 record, and then some of them actually, because right now, next one that we try to talking about is I want to know the entropy. And then what is the entropy based on my class? Class is this cheat. So then 1, 2, 3, 3 of them are yes, and 1 of them are no. So if I try to convert them to probability, then you will find out there's a class of the no and a yes. That is 0.25 and 0.75. You might ask me, Professor, why not doing the entropy 0.75 and then 0.25? Because they are the same. So right now we don't really care about order. But when we try to calculate them, we will get the entropy called 0.81 for those 4 records, because 3 of them are yes and 1 of them are no. Okay, so then this is my parents' note when they are actually marriage status is not married, so single and a divorce, we will get this part. And then afterward, so you can say after that, my original parents attribute, when they are single and a divorce, my entropy is 0.81. And then I will be able to calculate. So when I actually have the tax income, and then right here you can see these branches, tax income less than 80K. So who are less than 80K? This and that. I'm sorry, it shouldn't be this one. It should be less than 80K are right here. This one. Okay, so then you will find out there's only 1 record. So in the end, the entropy is 0 because it's totally classified to no. And then who are bigger than 80? Bigger than 80 will be 85 and 95, 85, and 90. So the 3 elements, and then they happen to be all yes. So entropy will be 0. So you can actually see if I choosing the tax income and utilize 80K as my threshold to partition then afterward, then I will get my information gain of 0.81 minus 0. So that will be my information gain. So I'm hoping by giving you a more step-by-step example, you do understand what is parent and what is parent attribute. Okay, so then next question. Actually, some students are they are saying that I still don't really understand the test of significance. It's still too confused. Okay, what does that mean? So in the test of significance, we mentioned this term and another term called confidence interval. And then last time we also say the confidence interval actually you can depends on how much confidence parts that you want to emphasize. It's like 99% of the confidence or 95% of the confidence. It actually are related to how much area that we try to cover. Okay, so then imagine that if I have 2 models, assume I have 2 models, and then the first model, A, right here, you can see this is a bluish, blue-gray, this shadow. And another model actually is like light purple shadow. And based on their confidence interval, like 95%, you find out these 2 range actually did not overlap. So if we have a case, like there's 2 model, you calculate their confidence interval and find out they are quite separate. So which means that you clearly know that one is better than another. So assume right here, this is certain talking about how good or how bad they are, and then right here, then you are knowing that they are just so separate, and then we knowing to go to this direction is better, and this direction, another direction is worse. So you can actually see that this purple one is much better than the blue one. Okay, and why is that important is because assuming if I try to give you another shape right here, you can see there is a very light blue in the front. And then you will find out that this gray blue and the light blue, actually they overlap. And which means they're having few part, like this one, I'm trying to circle. They overlap to each other. So which means that in certain place, I have difficulty to differentiate these two models. And then we also know sometimes if I only have a mean, okay, so if I only have a mean right here, so let me try to change my color. So you can know that the highest point right here are the mean. High points right here, they are the mean. So then I actually utilize this thing to calculate few different points. So this one is like 0.1, 2, 3. From the mean, you will know 3 is better than 1. You will also know 3 is better than 2. From the mean, you know 2 is better than 1. But if we utilize test of significance, we know they do having some range from the 1 and 2. They are kind of overlap. So we don't know does the 2 better than 1 might be some hallucination, some illusion. Maybe that result is the 2 actually is getting higher just because they got lucky. Okay, because if we actually sample in a different way, maybe today we were changing the result. So then we are not that confident. So test of significance is like try to see does the method itself, the difference between the method are significant enough. Like 1 and 3, they are significant enough. Okay, and then maybe I also forgot to mention. So why we actually talking about the range? Range means, okay, so I again go back to this range. So then, for example, right now you see this Z 1.796 and 1 minus alpha is mean 0.95. So then when I actually having that, which means this range, I'm pretty sure that 90% of the time, my result will be fall into this region. Yes, it will be still possible that we might having 5% of the chances they are located in this white region. So in other words, you will find out if I have 0.99, then you will find out the area actually is a little bit bigger than the 0.95. And then they are bigger, so which means that interval is also larger than 0.951. Okay, so then I actually can almost sure, like if this one today is 99%, and then cover from right here to right here, I'm almost sure there's only 1% of the chances it did not fall into my prediction, but 99% of the time that my element will be within this region. So I'm pretty sure it will be within right here. So if that is the case, it's like 99% of them, they are all information right here, and 95% of them, they are in this region. So we did not see the likelihood that is two model overlap. But then in these cases, it's because we could see that there's some range. Here are some range. This range means that I had chance that these two models are not one better than another. Probably the light blue actually could be even worse than the gray blue. Okay, so then we utilize test of significance to double check about that, to make sure that our results are not being shown based on the luck. Okay, so continue that you will also find out that in our equation, then we having a number called n. So we have this n number. Okay, what does that mean? It means the sample size. And then I try to draw the figure for you to understand. Okay, so then from the statistic, all the record that we try to talking about are based on some probability concept. It say that all the element, actually, if you just try to toss a coin, it actually probably will give you a positive side, and then toss or like you were having like a face, or like the text side. So then you actually draw as many as possible, then you will find out in the end it will closer to 50% and 50% of the head and the text. So for example, that is based on probability. So you can actually see when the n is bigger, okay, it actually getting closer to the mean that we try to talking about. So if the n is bigger, so for example, like right here, we are going to tell you, if my n actually is bigger, and I say my average is 0.8, you might find out that it will not be like right here, this n right here is 1,000 sample. So based on the 1,000 sample, I told you that the average is 0.8. I can somehow quite sure it's really most of the value, the accuracy probably really are around 0.8. So you can actually see there's a region, actually this region actually is a little bit smaller than other side. So you actually can see if I actually n is smaller, n equal to 50, and then you will find out the range is a lot larger than the red one, the n equal to 1,000. So this is for green, and this one for purple, and this one for red. So you can actually see with the n getting bigger, our confidence interval actually is just getting more narrow. So of course, the bigger n actually means more accurate and more confidence. I have more confidence. Okay, but if your n is quite small, then you will find out that we are not really sure about that, because we still try to test. So I hope that example allow you to understand that why in the test of significance, we need to utilize the n. Okay, why the sample number matter because of that. Okay, so then there's another question. Some students say, I still don't understand. I mean, not only one student, quite many students say the confusion matrix are still a little bit too, professor, you talk too quickly, or like I don't understand how we try to get it. First, we try to show you this confusion matrix last time. Maybe I just go through them very quickly. And then what is phi? I just count. Based on my output, I count how many elements I predict them as depression. And then I got phi. And that phi actually is, I know their true label are depression. They are phi. So just assuming this matrix, I try to predict the patient's mental status. And then some of them are depression, some of them are healthy or normal people, some of them are bipolar people. So then based on my prediction, so then here, this direction right here, so the column attribute represent that are my prediction. And then the row, this label right here, means based on my actual label data, based on my correct data. So out of my prediction, I predict, so you can actually see right here, based on my prediction, 7, I predict them as depression. But among 7, then 5 are really depression people, and 2 are bipolar people. So this is example. So then I actually can say that right here, I have 32 people. They are being highlighted, or they're being marked as healthy people. Among them, 27 people, they are really healthy people, and 2 of them are actually, they are not healthy, they are depression people. 3 of them are bipolar. So etc. So you can know right now the 5, 2, 1 are not, I do some weird equation to get that value. No, it's really count how many elements fulfill that category. And then, so based on that confusion matrix, let us try to give you more example. So for example, today, if I want to count the precision for depression, how I count in this confusion matrix, I pay attention to here. Okay, this column. Okay, because precision is mean how accurate I no, how correct I predict. Okay, so the precision is based on my output of the prediction. I mark them as a depression, and what is the percentage of them are correct value. Okay, and then the recall actually is different. So precision right here, you can say, then I have 7. Okay, 7 out of the 5, they are really depression. So you can actually get a depression value is 0.71. Now, how about recall? Recall is actually, so based on the depression, recall actually is this row. Okay, recall means among all my real depression patients, how much of them are being accurately or like correctly identified as a depression patient by my classifier. That is called recall. So then you actually, based on that, you calculate this row. So 5 plus 2 plus 1, and in the end you got 8. So 5 divided by 8, you got 62%. So then if you still do not understand that, let's try to go through them a bit slow. So how about healthy people? Okay, healthy people, the prediction, again, check the column. Okay, and the recall, check the row. And then when we try to do the bipolar, again, check the column. And when we try to find the recall, we check the row. Okay, so that is based on our example, what is precision, what is recall. And then, so some people actually heard about certain thing called micro precision. What is micro precision? It's just we adding up all the thing together. So we adding them up. And then afterward, we got my precision. So I don't really care about which label I'm talking about. I just want to know how many sample I have. So I add this 5, I add 27, I add 6, because right here, 5, 27, 6. Okay, so then after that, right here, I add 7, 32, and 10. So you just try to adding the number right here, and then you got this value. So this one is called micro precision. You might find out I don't really care about is that okay, because some classes probably is bigger, some class probably smaller. No, I don't care. I just adding the number up and then do my division. So that is called micro precision. But some precision is called macro precision, saying that no, it's not really fair. Why it's not really fair? Because we can actually see some class actually is bigger, some class is smaller. If you actually pay attention to my original precision, you will find out that the value are very just different, very different. Because from the 0.6 to 0.84, a very wide range. Okay, and the micro precision is I don't care. It's just adding them up, and then you're getting this value. So when you see this value, let me try to give you some small test. Try to see the difference. 0.78 to 0.84, that's 0.06. And from the 0.6 to 0.7 is 0.18. So you will find out that my micro precision actually is closer to my healthy categories data. It's far away from my bipolar's data. Why? Because I don't really care how many elements in that class. right? I actually just try to separate all the class, and then I try to adding them up. So in the end, my micro precision will having the tendency, and then will be closer to the class value. That class have a bigger amount of the volume, because this healthy actually have more people. So in the end, it will be closer to healthy. Micro precision is, let me try to treat each class equally. I treat them equally. Okay, so which means each one of them share the same weight. So then what I did is I did not directly adding up the original row number. No, I pay attention to the calculated precision. 0.71, 0.84, 0.6, and then I try to adding it up and averaging them. So that is become 0.72. You will find out this value actually is not as close to the healthy category based on that case. So that is a micro precision and macro precision. And we can also do the same thing for micro recall and macro recall. Okay, so I think this is a wrong number. This one is called recall. Recall. Okay, I did not do that correctly. Recall. Let me try to correct them. Okay, so this one is recall. Okay, so I'm hoping for that people to understand about this confusion matrix. And then we finish about the QA, and let's come back to the evaluation. And last time we utilized confusion matrix, and today you know that's how to calculate about this precision and recall. And then this time we also would like to remind you something. They are having some limitation about all the measurement. Please also remember there's no any method are completely correct or completely just strength, no weakness. No, all the methods have their corresponding limitation. So what we usually did in the data mining is we need to understand the limitation of those methods. And then we know that limitation actually happened because of some of the reason. So then we, in that kind of scenario, that we don't apply that particular method, because we know if that method encounter this scenario, they always show the limitation. So we don't apply them. The reason we try to choosing or like study so many different methods, and want you guys to know the limitation and the limitation or strengths about that, is because we hope it can make you to having a better decision when it comes to your time to make a decision, say which method I'm going to use. Okay, but then which method we are going to use actually will also depends on, do you know the current situation? So how do I know the current situation? I need to do some evaluation and know where I stand. And based on that, I make my next move. Okay, but then they're do having some practical issue in the classification. The first thing is underfitting and overfitting problem. Okay, before we go to the underfitting and overfitting problem, I would like you guys to go to the NTU Cool and then working on that problem. Then say that which one is underfitting, which one is overfitting. Okay, so when you listen to this recording part, please pause it a little bit and then do the exercise first, and then afterward you come back. Okay, so maybe this method or this concept are not that new. If you already took some similar courses before, you already know what is overfitting. So let us try to see this figure to illustrate what is overfitting, what is underfitting. Overfitting means you learn too much. Underfitting means that you still can work harder. That's it. Okay, just like I'm not so sure. Do you have that experience that when you do this, when you try to study for high school or something like that, and sometimes after the exam, you get the grade back to the parents, and parent actually will see your transcript and see your number, the number right there for each grade, and maybe some parent will tell you you need to work harder. Okay, so if you actually having that impression, which means that is called underfitting. Okay, overthinking is totally different approach. It's like actually you did not really do well, but then but people don't know that. Sometimes it will be quite interesting. People confuse between overfitting and underfitting, because in the end, no matter they are underfitting and overfitting, they all show in a way that they did not perform well. Okay, so then how do we know you did not perform well? Let's try to see this curve. We have two different curves. One is training curve, one is testing set. So let me try to utilize the real life example to illustrate it. The red line represent in a way that you, for example, you are going to have English exam, okay, and you get your textbook, and the textbook has so many exercise. So you're working on the textbook, working very hard. And textbook, this exercise, you're working on them. And then if you get something wrong, and then you come back next time, try to redo them, do that over and over and over. And then afterwards, so you might actually in certain stages that all the exercise in your English book, English textbook, you do them correctly, nothing wrong, because then everything you this exercise you already do them for 2 times, 3 times, 4 times. You kind of already memorize that in your heart. Okay, so that textbook of the exercise question are just training set. Okay, so you know the training set is something that you learn. Okay, you have to learn through that textbook. Okay, testing set is you learn it, and then next day is the midterm time. So you're having this 月考 or midterm. You go to the classroom, okay, and the TA is starting to give you the answer sheet, the question set, and give you an answer sheet, and then you're starting to write them. Is anyone actually having the problem? It's like, I don't really know the answer, okay? And then you just look at it, say, oh, I think I know the answer, but in the end, you fail to give the answer back. Okay. So in the machine, we actually can do this, to record how the test being conducted and how is the outcome. So then we actually try to show this one to you. The x-axis right here is number of nodes. So number of nodes in the decision tree means, okay, here we try to utilize the example in the decision tree. This is one of the decision tree. So you can imagine that we have 1, 2, 3, we have this attribute node. So then this decision tree have 3 nodes. Okay, and then but so right here in this example, we say that we have number of nodes is from 0 to 300. You can imagine 300 is a tree, very, very complicated, so many nodes. And then we want to know that if my tree actually is bigger, very, very complicated, will my result getting better? And the answer is yes. You actually will see your training set right now. So you can utilize a real life example. What is this nodes? Means that the number of time you practice, the number of time that you practice about that particular exercise question. So the more you practice, of course, and that you in the end you memorize most of the stuff by heart. Okay, so training set, you will find out that the number of nodes mean that how much you try to break through them. And then the bigger the node, the number of the node is, actually the training set actually getting better and better because the y-axis is our error rate. It's just getting better and better. Okay. Then right here, we're going to show you this blue line. This line right here. We say that our test set. They are the one that we try to know. Okay, so you having so much node, or like you learned that for many times. But then when you go to the midterm, we try to give you a question you never saw, never have seen before. This is the first time you've seen that problem. But that is the first time we want to know how much you understand, real understand. And then you will find out that if we have a curve like this one, which means that they do having some parts. So for example, let us try to go through this curve. And then you will find out I try to draw a line. In the bottom of the line right here, probably this point. And after in this point, I actually can partition my figure into the left-hand side and the right-hand side. Left-hand side mean right-hand side mean overfitting. Left-hand side mean underfitting. So what it means, you can actually see the overfitting part is the better I remember, the more I practice, my result getting worse and worse because my testing set, this test set right here, actually you will find out the error rate just getting higher, which means that is not good, right? And but then the underfitting is like when I actually practice more, yes, my error rate also drop. So then if you are right here in the 50, then you actually in a mode that is called underfitting, which means that you can really improve. But then if you are then right here, 200, you are in a mode called overfitting. It doesn't mean that you did not work hard. It means you work too hard. But sometimes in human being, we have difficulty to know that we are really underfitting or we are overfitting because we just get this transcript and actually tell us that my grade for that topic is 50. How do I know this 50 is overfitting or underfitting? When you learn the machine learning or data mining, then you will know. Actually, we have two different approaches to deal with that. One is work harder, spend longer time in that problem. Next time you try to see if you do that, the grade will improve or not. If the grade is not improving, it's just getting worse, then you will know that it's overfitting. You should reduce the working time because you work too hard. Okay, and in the decision tree, what we need to do is like, for example, I get an error rate of 35%. I don't know. That is, I need to study harder or like not study hard. So then I actually will test on it. So then how can I make the number of the nodes from the 200 to number of node to become 100? You can cut the branches. So for example, like right here, still in the same branches, right here we're talking about. Assume we say that right now this tree is overfitting. So what we need to do, we might need to do one thing is, for example, I will decide, let me try to cut this branch. Because with these branches, even though they look good in the training data, but when I have that branches, it actually just make my testing data not good. Okay, so that branch need to be cut. Okay, so in the decision tree, we were talking about cut the branches. Actually, in the machine learning related course, like in the classification, the similar concept can be adopted. In your neural network, it means that you cut the node, cut the neuron that we're talking about. And in the Naïve Bayesian, actually is also talking about how many branches right here. So we also cut the branches. Okay, so that is a concept about overfitting and underfitting. And the next one, we want to let you know why the overfitting happen. If study hard means it's important, why study harder in the end is a bad thing. In the machine learning part, we will tell you overfitting probably is because of the noise. I memorized too well. It shouldn't happen. There's something I make a mistake. I believe most of you guys, when you're working on your lab 1, you already received the clarification from RTA. And thankfully, some student bring up the issue, saying that why there's a 2 label, which one I need to follow, why there's some inconsistency. Yes, in the real data set, we do find out something like this. Okay, and then we are very glad some people actually realize actually noise exists. There's no any example we can guarantee they are 100% clean, even though some people already try to clean them. But in that cases, if you memorize too well in your training data, during the testing data, you make mistake. So overfitting might be because of noise. Overfitting probably is also because then I thought I tried to cutting them very well, but then they do having some example, they are being misclassified or that there's certain information I don't know. So then when I actually in the testing data set, they actually know the information, and then in that cases, then I actually find out the way I try to train is in a different direction. So how to avoid the overfitting one? This scenario in the classification, there are 2 approaches. We already talking about them, pruning. So no matter what they did, pruning. But then right here with the 2 approaches, because one of them is trying to cut them in advance. So we call them pruning. We don't finish constructing our tree till the end. We cut them in middle of the way. Okay, but the difficult part is, like you might say, how do I know I need to stop? Actually, in the real life, we don't really know. So in some company, if there are certain example that people already know them very well, so expert might tell you, I have some sense to knowing that. But most of the cases, we probably do the post pruning is better. Post pruning, the one they are not that popular in some paper is because it just look like try and error. You try to go for a full-grown branches, and then after that you try an arrow to cut the different branches to see which one looks better. But post pruning actually is easier for us to execute. Okay, so then here we're already talking about the decision tree, but the next one we want to let you know what are the limitations of the decision tree. We want to utilize this example to tell you that decision tree actually looks like some partition. You can imagine they are like a linear way of the partition of our data set. Each branches are just a partition. So this problem is okay for the decision tree. This problem, we can also utilize a linear way to do the partition. But this problem have difficulty to partition them correctly. So decision tree actually are useless in a way that if we find out certain attributes are correlated, they will have a hard time if I have correlated attribute. But I hope by listen to that, you will understand that how important it is to do the pre-processing, right? If we can do that very well, correlated attributes supposedly should be removed. We should do some subset selection for my attribute. Okay, but then usually in our real life, it is different. It's very hard to tell for some cases if you don't really know them. Okay, so that is a summary for decision tree. The advantage is it's quite easy for us to understand why the decision tree look like this, because you just have the branches and easy to generate the rule. But disadvantage is it will suffer a lot from overfitting. And then your we just told you the decision tree more like a linear way of the partition, so rectangular way of the partition. So if you have features that are correlated to each other, they cannot do well. And then you might need some pruning to alleviate the overfitting problem. So don't and also they cannot handle the streaming data. So if you don't know what streaming data is, means that the data keep coming in. The decision tree is good for the data they are static. They just stop. Okay, then you work on that. If the data keep changing and keep updating, then you try decision tree might be difficult. Okay, so we finished about the decision tree. Okay, so we have finished the part about decision tree, and next we're going to talk about the random forest. Random forests are usually a variation of the decision tree. With decision tree, as we discussed, you might need to grow the tree in a very, very large scale way. And then you don't know exactly where you should prune. Random forest was introduced to address this issue. At the very beginning, we need to introduce a concept called bagging. Some of you may have already heard about this term in machine learning courses. Bagging stands for bootstrap aggregation. So some people probably also call them bootstrap aggregation. And what does that mean? The basic idea is like what we did in a democracy. We have every different individuals, in the case, trees, and we let them vote. The majority win. That's it. So how do we generate this different tree? We use a technique called random sampling with replacement. Let me give you an example. Suppose right here we have training data and testing data. And then in this training data set, assume we have 1,000 sample. Instead of using all 1,000 sample for a one tree, we randomly draw, for example, saying 400. And with replacement. So then we draw something from the training data set. And then after we put it right here, and then we put it back. So that is called randomly sampling with replacement. And then we draw another sample for 400 sample. And etc. etc. So you might see that the subset of my sample might overlap, but each gives us a different data set. For each data set, we build one decision tree. So for example, if we repeat this process like 10 times, we end up with 10 different decision trees. Each tree gives its prediction. And then so right here, so for example, and this tree say A, and then right here say A, and then etc. etc. And then this one say B. So during the aggregation part, then we say 6 tree for A, and 4 tree go for B. Then the final answer will be A, because the majority win. This is the main idea behind random forest. Notice that the bagging, this concept, is a very general concept. It can be applied to many machine learning models. Then right here, the model could be different type of a model. It's not necessary only being for decision tree. But when we having this bagging and combined with the decision tree, we call this method random forest. Okay, random forests have another interesting twist right here. In normal decision tree, we split them, no, and we consider all the possible feature. But in the random forest, and we might actually consider some subset of the feature. So not the total complete set of the feature, is subset of the feature for each split. This might adding some diversity among my tree and will likely to reduce the problem of overfitting. So each tree is not only trained on random sample of the data, but also based on random subset of the feature. In the end, we agree their vote to make the final prediction. So that is the concept about the random forest. And then you can also know that the very nice things about the decision tree and the random forest is because it's very interpretable. Each tree gives a set of the rule. So for example, let me try to go to one example of the tree. So assume I have a tree, like right here. Okay, so this rule would be say if this value, like this refund, is yes, then you go right here, and if not, go right this part. So each node right here will be able to give us a rule. It's quite easy for a human being to understand since we often make a decision based on this logic rule. But the modern machine learning, many models are not that easy or not that transparent for us to see. Sometimes we know the answer, but it's hard to explain why the model would make that decision. That is why that when we're talking about the random forest, we're talking about the random forest right here, and then those randomness is a very important concept because repeating the random experiment many times, maybe the truth in the end will be emerge. Having an example like thinking tossing a coin, we might not know the true probability at the very beginning, but we toss it enough time, the result will show up is about 50-50. So then because of that, we would like to that you know that that is a concept when people talking about that. Sometimes in the machine learning, we probably know the answer, but we don't know how. So by utilizing this randomness or utilize this probability concept, we might likely to get the result. So this leads us to our next topic called naive Bayesian classifier. Okay, so now let's move on to another very typical method in machine learning. It's called naive Bayesian classifier. It is based on Bayes' theorem, named after the person Thomas Bayes. An interesting thing is Bayes himself lived in a time before computer even exists. He was an 18th century person, and some people speculate that he was motivated by question about miracle and a faith during this Enlightenment period. Around that time, many people believed in miracle, but some people actually think that is not true and thought miracle probably just for luck or some coincidence. Bayes tried to bring the mathematics into the discussion. He wanted to utilize probability to evaluate the likelihood of the event and the testimony. So as you can see, Bayes' theorem gives us some rule, some mathematical framework to update our belief when the new evidence appears. This is why it becomes so important for statistics and machine learning. So let's try to see some practice about that. Utilize a very simple example. Suppose we want to classify the insect into different categories. One is called katydid and a grasshopper. To us, to me, they look very similar. One feature we can use to differentiate them is the length of their antennas. Okay, so imagine we collect so many data. Each time we measure an insect antenna, like right here, 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 and then here. Okay, and then we record their length and their type. Over all the time, we might notice that katydid usually have the longer antenna, while grasshopper usually have the shorter one. So that we get the distribution. And now we get a new insect. The antenna's length is 3. The question is this insect more likely to be a katydid or grasshopper? Okay, Naïve Bayes answer this question. They look at this question at a conditional probability. That is, by given a feature value, in this case, antenna length equal to 3. What is the probability to belong to each class? Suppose in our class, in our data, they have 12 insects in total, and they have the antenna length equal to 3. Among them, 10 of them are grasshoppers, and 2 of them are katydids. So based on it, the Naïve Bayesian will predict, or like conditional probability will actually say 83% of the chance the insect is grasshopper, and only less than 17% of the chance it is a katydid. So this is a very important concept or meaning behind the Naïve Bayesian network, Naïve Bayesian network, because it used the likelihood of the feature and for a given class, and it applied Bayesian theory to talk about the probability around from the probability of the feature to some class, because before we probably would say like this one. So here is a Bayesian classifier. And Bayesian classifier actually is construct from the conditional probability. But then they give us a very nice twitch right here. So based on conditional probability, I probably can write in this way. If there's conditional by given conditional A, and then I want to having the want to know that what is the probability of the class C, I can write my formula in this way. Okay, and in the reverse order, I actually can also say by given the class C right here, what are the probability of having that feature value A? So you actually can see that is a basic concept of the conditional probability. In the Bayesian theorem, actually they can tell you if I have the equation like this one, I can actually convert probability of A and C. So let me try to do this one, is equal to the probability of given C of the attribute A and multiply the probability of C. So you can actually see this is a simple mathematical equation change. So Bayesian theorem is, if we already know that, okay, based on these two equations right here, then by given the attribute A, okay, and then I want to know what is the probability of C, can be calculated based on by given the by having the probability of A and the probability of C, and by the probability of CA. You actually just find out that this is actually just coming out from these two equations. And one very important thing is because it's based on conditional probability. So it assumes the old independence about the feature. That is why it's called naive. Okay, and so remember our name at the very beginning is called naive Bayesian classifier. Why naive? because all the features are totally independent. Okay, and why is that important? Because it can simplify all our calculation. So why our decision tree try to give us an explicit rule. Naive Bayesian actually rely on the probability. You don't actually need to having some human beings say, oh, if this one happened, then what happened, then what will be the result. No, it's based on the likelihood we estimate from our sample. And based on that, the probability thinking actually is a very fundamental way for our current machine learning. Okay, so then when I finish about having the description, next one, it will be your turn to practice how to convert the statement into the Bayesian theorem. Okay, so you can pause this recording now. And after you finish, then we can come back. Okay, welcome back. Let's try to work on the example you work on in the NTU Cool and see if you know how to translate the statement into the conditional probability. And in the example we give that to you is a very practical example for Bayesian theorem. So assume given 1% of people have certain genetic defect. When we try to represent them in mathematical form, it could be written like this way. So X will be equal to the having some genetic defect, so which means they are positive for the test result. And then, so 1% of the genetic pattern right here. So then you actually will say 1% of the people. So I actually can say, this is genetic fact right here. So I can write PG equal to 1%. So then you actually can directly write another statement, say if that is not this genetic defect, so P not G will equal to 1 minus 1% equal to 99%. Okay, so this one is we're done with the first statement. Let's try to go on for the second statement. If a person have this defect, 90% of the tests for the genetic defect detect the defect. So how we try to write them? So based on that, we say it will be positive test result is called X. So if the person has a defect, so the person of defect is like G, okay? When you given G, what is the chances of X? And this statement, they say 90%. So this statement actually combined with the X and PG right here, we can write something like that. So then we say 9.6% of the test result are false positive. So then we can actually know false positive, which means they did not having that genetic defect. We can written in a way saying that by given non-genetic effect and having the test result of the X will be equal to 9.6%. Okay, so together we can actually translate our language into this conditional probability form. So the question is, if a person get a positive test result, what are the probability they actually have the genetic defect? So then we actually need to say, by given X, so there are positive result, and then can I estimate PG? So then you can actually convert our statement and based on this mathematical conditional probability form. Okay, and how we try to do that calculate? We can actually base on, because we given this equation before, right? So we can mimic this way, saying that right now I want to get the P by given X, and what is the probability of G? And then based on that, we just try to copy paste right here. So by given condition probability of a PX, and then after that, I have the given PG, and by given PG of the X. So then right here, PG right here, you actually know that is 1%. Okay. And the PX by given G and of the X right here, this part is 90%. Okay. And PX right here, before we're talking about that, this is X. And then the probability of PX is actually by given G and after half the X, and by having non-G of half the X. So actually you can see that is how we try to do the calculate. So in the end, by combining together, we will get this one. Okay, so then that is the result of how we actually can answer this question. I hope that is clear for you guys. The next one. Then after you knowing this information, okay, in classification, we utilize the previous equation, previous concept, and to thinking about, okay, so each attribute, we're thinking about many different attributes, and we have the class label as a random variable. So when I have a record, I know their corresponding attribute, and my way is try to predict are they belong to certain classes. So we actually can maximize all the likelihood from by given all the attribute and then by C. So how we can estimate them? Naïve Bayes classifier right here actually are giving that equation. Okay, so you can imagine just based on the previous example, you know, we can convert that to equation and choosing the value and then try to estimate it. So then by simplify all the calculation, the best way for us is try to assume all the attributes are conditional independent. So we can directly multiply the attribute together. That is why in my previous example, you actually see I multiply, right? Because you might actually, when I talking about this question, right, this example, before you might say, wait, why is it multiply? Because we already assume they are independent. So when I independent, I know the probability of by given G of X, and then I know the probability of the X, okay, X, and then I also know something. So in the end, I can just multiply them and adding them up and become my result. Okay, so the same cases right here is if we actually having that concept, they are conditional independent, no dependency between all the attributes. So we can multiply all the probability I know, and then afterward, we just try to find the maximum likelihood. Okay, so by the way, right here, I can stop right this part for you to know that you just need to know what are the basic concept of the Naïve Bayes classifier. Don't worry, that's in our final exam. We are not going to ask you to do that calculation because it's supposed you should belong to your probability course, not right here. So then you just need to know that why the Bayesian network will work and what are the basic hypothesis or assumption behind it. And they are conditional independent, and then because of that, then you will know with all the attribute I can directly calculate the probability from my data set. I will say, oh, they're having like 40% of this class and then 60% of another class, and then I can also calculate from my data set knowing that how much probability that of having this attribute with that value. So you can imagine the thing I actually did not talking about is because all the probability right here can directly be calculated from my data set. And then after that, I just try to multiply them and then sum them up. Okay, so it's quite easy to implement because just condition probability and multiply them. As long as you know how to convert the statement, everything will be fine. And moreover, that we already having some package, some software, and already know that how to keep that information to you. You can go to Python, find the corresponding library, or you can go to many different kind of machine learning package to help you with it. And also the very good advantage for the Naïve Bayes classifier is it actually can serve as a very good baseline, which means that for majority of the case, that the result come from naive Bayes and classifier are good enough, like 80%, very good. Okay, so you actually can also see from like many Kaggle competition, they usually give you the baseline. Where the baseline come from? Most of the time come from naive Bayes and classifier. But the disadvantage is you need to assume those independence, class independence, attribute independence. But in reality, the dependency among all the variables are rare. Okay, for example, in hospital, then if your profile have the age, family history, and something else, you will find out some of the attribute might correlate it. Okay, so for example, you having the symptom of the fever, cough and thing, or disease of the lung cancer, diabetes, and so many things. Some of the symptoms actually will be found in the different diseases. So they do having the dependency among many different attribute and many different class. And it will be having the difficulty to model based on naive Bayesian classifier. So how can we deal with it? We go through the naive belief network. So I probably say something wrong. So if you heard I say wrong, it should be Bayesian belief network. So if you see network right here, will be more advanced. And the Bayesian belief network, why it's called network? Because it will try to allow us to relax the independence assumption. And then how we try to model them, we utilize some graphical model and to construct and all the dependency among the variable. And then afterward, when we try to construct this Bayesian belief network, this network right here, and then for each age, we were given some very spatial and spatialized probability distribution for them. And then because of it, the Bayesian belief network actually can encode the knowledge. Who encode them? Most of the time probably are the human experts try to encode them. And they will give us a better probability, and then we're having some each more accurate result. However, that is a however. Having a human expert to give this dependency and being given to the network, or actually try to specify what are the possible contribution, somehow they are difficult. Because most of the time when we try to do the machine learning, we are not the expert of that domain. So we might have the difficulty to know how to decode them. That is why Bayesian network actually is being proposed. But you actually can see in a lot of competition, then people don't really rely on it. Why? Because we're having something easier. So then here is a demonstration. We try to show you it could be done, but I have no intention to give you the clear idea about how I try to go through that. We just let you know it can be done. The reason we did not emphasize on it is because we want to go for the next subject called neural network. Okay, so now let's try to shift to our attention to the neural network. Neural network actually can be considered as a combination between many artificial neurons. So you can imagine right here, each one of them are neuron. And each neuron receives some input. And this input actually will be multiplied through their weight. So you can imagine like right here, I have neuron, and they have different input come from different place. I actually will know maybe, for example, this input, let me try to utilize different color. This red one probably is more important than the rest of the green one. So I can assign a higher weight to it. So that is the input for this neuron. But artificial neuron actually is not only that. they also associate with the output. So the output is they just try to sum the weighted input. Okay, so for example, like this one, they have the weight of 0.1. You just imagine the yellow one are weight of 0.1. So I have 1, 2, 3, 4, 5, 6, 7. And the red one actually are like 0.3. So then when I try to sum them up, it become 1. And then the input value actually, for example, this one will give like a 0.5, this one give 0.4 and something like that. When you sum them up, just assuming when I sum them up, you get a value of 0.85. And today I will tell you that I have the threshold. My threshold is 0.6. And then before I say when I try to sum it up is 0.85. And 0.85 is bigger than 0.6. So then I will output 1. If I actually did not get 0.85, I got 0.55, even though there's only 0.3 difference. But then, because 0.55 is less than 0.6, so then I did not output anything. It just becomes 0. So then you actually can see when I exceed certain threshold, I got 1. If I did not, I got 0. Okay, so then afterward, our neural network, most of the neural network, is try to program based on all the adjusted weight and the feedback from an example, and then I kind of fix it. So the most famous example for the, not famous, I mean very early on version of the example is called perceptron. So you can actually see this is how the perceptron might look like. And from the flowchart way, they have different input, and then they also each weight have the corresponding weight. And then when I actually try to sum them up, and my y that is trying to report are they belong to class A or class B. So for example, this one corresponding class Y. And if that is bigger than certain threshold, then the Y actually will output that, yes, that is belong to this class. So you can imagine the perceptron is just like this way. But then people actually find out, okay, I need to continue to talking about the story. The people actually find out that perceptron cannot solving a very simple exclusive OR problem. I think I actually mentioned them in our beginning of the session. That you can imagine the input right here is just like question. Okay. Output right here is like you expecting some answer. And from the question to answer, we did not give a very large learning space for our perceptron. So then, perceptron actually they've been proposed, and a few years later, some researchers already wrote some article, some paper, say that perceptron actually is not good enough because it cannot even solving a very simple exclusive OR problem. Because of that, neural network actually has been faded for around like 10 years, till some other some other researchers try to adopt for the neural network. They try to design certain thing called backpropagation. You can imagine like from 1980 to 2000, backpropagation is like mainstream for the neural network. And what they did is they are not only having input layer and output layer, because back to the perceptron. We only have input and output. There's nothing in between. So that's why I say very small learning space. But when we go to the backpropagation, we have input, we have output, and then we add hidden layers. You can have more than 1 or 2 or 3 hidden layers. Could be very, 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 very big. So many deep learning concepts actually come from how many hidden layers you will allow to have. Okay, and then afterward, you can imagine, except for input layer, I understand because I input and I told you what are the attribute value right here. And then output, I know what is the class. And all in between, they look like black box to us. We don't know what's going on. Okay, and because we don't know what's going on, there's no way for us to talking about why this input actually can be classified as output Y or class Y. Why? No one know. Okay, and but our neural network probably, so perceptron, that is the equation. Okay, but then afterward, a lot of neural network framework actually having more fancy equations. So for example, right here, I try to show you the backpropagation version of their structure. So they are not just these two simple equations anymore. They have more equation in between. Don't worry, you don't need to memorize them because they are not that like that anymore. But you can actually know why they've been called backpropagate. Okay, before we call them back perceptron. Why they go backpropagate? Because this is input file, right? This is input. Okay, when I actually output my result, but then it's wrong. So it shouldn't be this class. It should be this class. Okay, it should be, for example, it shouldn't be B, it should be A. And then you will generate an arrow. So then you can actually see there's an equation. Before you did not see any equation right here. But then right here you see the equation. And the reason they call backpropagation is the arrow actually is being identified at the output layer. But it will be propagate back. And so all the neuron actually will share and talking about how much arrow I had. Maybe I need to change this much, and maybe you need to change this much. So they will actually be trained. During the training process, we utilize our training set to adjust all the corresponding weight. So that is a process why we call them back propagation. We propagate the arrow back to the original node, like the input node. So the arrow, so you see when we're doing the training, we're starting from input and then go through the direction, go to the Y. Let me try different color, maybe it's easier. So during the input, we follow the yellow arrow and then we try to know where should I need to go to this result, go this far, and then go right here. But during the training process, we also have backpropagate. So there is the arrow happen right here, arrow happen right here. We propagate the arrow. By propagate the arrow, we change the weight, and we change the weight. And then when is the time we finish the training? When we find out there's no way for us to improve our accuracy, we stop. If you want to know more neural network concept, okay, then you can take the machine learning courses. They probably will go through all the equation. But then today, we just want you to know that what are the training. So the training is we input a lot of training sample. And then afterward, we try to see, we stop in a way that most of the tuple can be classified correctly. So at the very beginning, we trust the randomness and having so many random value, and we fit the tuple into the network one by one, and we compute the arrow and update the weight, and then we come back again and then training this one, update the weight, and come back to have the arrow and come back this one. We do this one many times until all of them are converged. Okay, so that is the network training part. And if my train too well, so a neural network also will be afraid of overfitting. Why? Because we might also train too much, memorize too much. So all the decision tree, the why they actually having the overfitting could possibly be appear and at the time when we're having the neural network. So then you can also find out they having different type of the neural network being proposed. And some method actually being proposed because they just want to make the pruning more automatically. They may actually having the way to pruning during the middle. So that is possible, but we are not going to be talking about that. You just need to know that is the basic flow about the neural network. But then next one, let us try to go for this NTU cool and for you to know what are the possible limitations. Okay, welcome back. This year, because we have this session in recording, so the way we try to participate for the brainstorming will be different from the last year. And we give you this NTU cool exercise for you to think before I talk about the answer. And because when I record this session, at the time when I record this session, I don't have any student to do this quiz. That is why you will find out for many quiz I asked you to do, but I did not explain, or I directly use a slide to explain because no one actually answered that question before. And for example, like this question, then we don't even having this quiz before for last year. Okay, so let's try to go over this question because you might, some of them might a bit quick, tricky. So which of the following are common limitation of the neural network? We try to select all that apply. The first one, it can be difficult to interpret or explain. This is true. We mentioned that neural network often being treated as a black box. All the internal ways and the layer make it so difficult for us to explain why the model actually are good, could be predicted in this way. Remember, right here I'm talking about the common traditional neural network. But then maybe recent year, they do having the different type of the neural network. For example, they actually being utilized for the image processing, and then they might utilize image way to explain. But then right here, we are talking about the traditional, that like more backpropagation neural network, the model without all the new advanced technique being introduced. So around that time, people consider they are a black box. But even for right now, for example, we have the our large language model are neural network based, but then we still have difficulty to understand why this weight actually look like this. So in general, they still being treated as a black box. Okay, second one, they can only be used for image recognition tasks. This is wrong. Okay, because as I just give you the example in the previous answer, then the large language model actually is not just image recognition. So it can be very general purpose, can be in natural language processing, can be in game, like AlphaGo, and then they can be forecasting, they can be utilized in many, many different applications. So not really need to limit it to image. The third one, they often require large amount of label training data. This is true, very true. Because before, if you see all the neural network, all the weight, how the weight being transformed and being adjusted actually require so much amounts of the training data to give them enough variation to understand how the weight can be tuned in a better way. So they really require a very large amount of the data. I remember when I learned neural network, maybe let's see, 30 years ago, learned the neural network, my advisor actually gave us a guideline. He said that you just calculate how many ages in a neural network. So very safe way to know how much training data we need to have. You could actually just multiply the number of the age with 10. Then that would be the example you need to have. We can also give you some example. You know why from like the AlphaGo or many things, why those neural network or like a machine learning method or AI actually starting to arise and then give people's attention? Because they actually come from one very important competition called ImageNet. Okay, ImageNet actually is Professor Li Feifei. Around that time, they're working with the image. And they find out each researcher they only have an ability to collect very limited image data. However, with all the neural network model we need to use, we require a larger training data set. So she actually tried to write so many proposal and asked for different industry to fund for that project. Fund for the project to do what? To having the image and to having some human to annotate. Oh, this image contain cats. This image contains something. And then afterward, they collect so much image data set and then hold a competition called ImageNet competition. Then afterward, then the first winner actually they utilize a model or like a framework that is called CNN. We're going to introduce later in my later slide. And why? Because they find out that, oh, with the CNN, you can do a lot better than all other different framework. So then starting from there with a larger data set, and then the researcher will finally be able to do their work. Not only than that, so for example, how the large language model becomes so important, it did not happen for a chance because before, if you know the large language model, then people might tell you they have so many different important projects going on. And one of the very important project is Wikipedia. Okay, so for example, if you try to find something right here, okay, want to know what is machine learning? You go to Wikipedia, they give you a lot of information right here, so many texts. So human being, actually most of them are like expert human being, try to edit the text. And then afterward, you actually can know the different relationship. You can see right here, we have different link from one to another thing. And the researchers try to utilize that text to help us to construct better thing. So Wikipedia and also like Google, if you go to the Google, why Google actually do something very well. So anyone know this Google Books project or Google Library? I've just randomly type of some book. So for example, you go to this Google Book project. Like for example, you don't even need to know what this is. But when we try to go in on right here, we have the text. And Google, this library, before then, they just try to preserve all the text information, all the library. So they have so many books. And then after they having that project, and human beings have a bunch of the training data that allow them to train the good information. So then really training data is one very important thing. Okay, so let me see my slide right here. Okay, so then this part, the third one, they really require a large amount of the label training data. So we give you two examples, ImageNet and all the Google library and so many things. Okay, so the next one, they are computational expensive to train. This one is also right because it requires so much of the data and you have many nodes. It really takes a lot of computation. So the first one is right. And the fifth one, they always need manual feature engineer to work. This one is wrong because the good part about the neural network is they don't need human being to do that selection. The strength is they will exhaustively compute and to know which feature is more important. So they don't need the old machine learning way or data mining way. They just need, we're talking about subsampling thing, and the neural network way, they don't. They just put everything inside. But you can imagine why they can do that, because they are exhaustively do all the possibility. Okay, so they don't need it, but then they come with a consequence. The computation is quite expensive. Okay, the question 2 right here. Question 2 right here, what challenge does a neural network face related to data and generalization? Okay, the first one, risks of overfitting when trained on small and imbalanced data set. This is right. As we say, neural networks usually need large data. If you have very, very small data, you might suffer overfitting quickly because your model memorizes everything. They don't generalize things, they just memorize them. And also, if you have imbalanced data, because they were actually thinking that incorrectly, so they might cause certain bias to certain classes that have majority information. So then the first one is right. The second one, inability to generalize well to data distribution that different from the training set. This one is also correct because how they try to understand the information is based on the training set. If your testing data set is totally different, so you're shifting your domain, then you might need some other method called like domain adaptation. You need some other transfer learning. But when we're talking about this neural network, we do not talk about transfer learning. So in that cases, neural network usually will fail when your test data are so different from the training data. The third one, weak vulnerability to irrelevant feature in data. This one we did not mark that was right because it do the neural network actually was harmed, is vulnerable to the irrelevant feature in data. So it is not as weak. Okay, they usually are strongly related to the feature. But if you have so many irrelevant pattern or like so many things totally different from what we're expecting, just thinking about it is very similar to the second question. So it actually have the strong vulnerability right there. Okay, the fourth one, difficult in automatically detecting and correcting mislabel or noise data. This one is right because they don't know they are noise. Okay, they don't really identify. Okay, they directly just consider they are correct and then give you the answer. So yes, it's difficult because they don't really know what is noise unless you train it. And the fourth one, inability to learn from unbalance at any scale. It actually depends. It actually depends. Sometimes, right now in all our text data, we tell you that classification are more like supervised learning. But somehow neural network actually can utilize certain way to be more like a self-supervised or semi-supervised learning. So it could learn from unlabeled data if we switch in a way to make them to thinking that is supervised. Then that we are going to give you some example later when we try to cover the text mining. Okay, the third set of the question. Your practical deployment challenge right here. So which of the following are true practical challenge that limit the real world deployment for the neural network? The first one is dependency on the specialized hardware for efficient training and inference. This one is right, correct. That is why NVIDIA is so hot, so popular. And then when we try to, and also Trump is so angry to Taiwan because they're thinking about all the GPU, all the thing actually is being in Taiwan. So then your United States do not have it. And why is that important? Because all the training really, really depends on those hardware. Okay, so first one is straightforward based on all the political thing and the news that you know. Second one is frequent requirement to retain model from scratch whenever new data arrive. This one is wrong. Okay, why? Because we don't always need to start. So the part wrong. We frequently need to require to retrain. This part of them is right. This part of them is right. The wrong part is right here, from scratch. This keyword is wrong. Okay, because sometimes we can do certain thing called fine tuning. So, or like we can say it's called transfer learning or incremental learning. I remember before that I saw some paper or some talking about in medical in medical application, they don't have quite many medical record. Okay, for example, if I want to know X-ray of the chest, I need to having so many X-ray data. But not many hospitals were willing to provide all their data set. So at the very beginning, they do having the difficulty to start from scratch. So what they did is they get a bunch of objects. So for example, the glasses, the cup, the glasses, the iPad, and so many things. So they put so many ordinary objects into our their system and learn all the age. And after that, they transfer with a smaller set of the training data, transfer them to X-ray chest radiation check. So that is an example of the transfer learning. Yes, that is possible. So it is not starting from scratch. We can do fine tuning. We can do incremental training. We can do transfer learning. Okay, the third one, complete lack of available framework or tool for large scale deployment. This one is wrong. Okay, we are going to show you that example that they have so many large scale deployment or some tool like TensorFlow, PyTorch, and Colab, and TensorRT. So many Hugging Fast. They have so many different tools, and then all of them support the large scale deployment. Okay, so the third one is wrong because we do having some of the framework. Okay, the fourth one, high computation and energy cost. This one is right. So that is why many people say that the neural network actually are not environmental friendly. That is also the reason why some researchers try to working on some concept called green learning. Green 绿色 green learning. So, and what they mean is like, I don't need so many energy. I don't cost so much things because they can utilize more, they claim they can utilize more efficient model to learn. Okay, but generally, that most neural network model we know actually have a very high computation and cost a lot of energy. And the last one, latency issue in time critical application. This one is also right. So when we're talking about time critical, it means that our data probably come in the real time. Just you can imagine, like recently we do having the news, people actually talking about why the bank actually allow some fraud, some deceit, some lie actually can be happen. So all my money is being wiped out. Then that is not fair. Why this one cannot be blocked? Because the data come in real time. The action need to be taken in real time. But in that cases, you require like a millisecond or microsecond that the time for you to actually take that action. But the deep neural network model or neural network model, in order for you to fine tune and try to actually catch up with it, it's difficult. So then from that perspective, the time critical application might not like might not thinking that neural network model can help much in that case. But of course, you can solving with a lot of not so urgent case. But then for the very, very urgent cases, and then we might thinking that you need some other different mechanism. Okay, so that are about the quiz that I try to working on, and this one's new. And I think that if you go to TA, they even did not know because last year they did not having this questionnaire. Okay, so then afterward, we are going to talking about the convolution neural network. Okay, let's try to turn our attention to convolutional neural network. It's kind of neural network, but it is more interesting than the original neural network. Sometimes you might also heard people to call it CNN. Okay, and the convolutional neural network are originally inspired by how our biological visual system work. around 1960, and they're still having some researchers try to study the animals' vision biological mechanism. So then we call them visual cortex. Okay, this is a term. And then we actually discover that there are two kinds of the different cell. One is called simple cell, and then one is called complex cell. And it's quite interesting to know because simple cell respond relate strongly to the straight edge. For example, like in this image, you might actually see they do having some straight edge, like this line, okay, or like this line. So they do having some straight edge. Okay, so in any image right there, you can find this kind of combination. And the complex cell, actually, they have the larger receptive field, which means that they are responding to pattern. Okay. The pattern, for example, like right here in this cell, they are just ball, okay? And then you actually will find out the same pattern. The ball actually is being distributed at different places. So then, in other words, that is, if they actually find out some pattern in this image, and no matter this pattern is located at which location, it still can be detected. So that is called complex cell. And so after that, for like around 30 years, and Jan LeCun and his student or his colleagues actually is being inspired from that kind of study and apply this biological concept into their mechanism and for computer vision. So computer vision is you give me one image and I tell you that what are the objects located at this image, and then I will understand about some of the meaning or some detect certain object in these images. That is called computer vision. So then you can imagine the CNN actually is not a very, very new machine learning work. It's been invented even before 1990. Okay, and but then the reason that the CNN are not popular, they do having some reason. And so what is the intuition behind the CNN? So because just like the biological mechanism that they have the simple cell and a complex cell. So then Jan LeCun and then his colleague actually were thinking about, can we utilize the similar approach? Because before, when we talk about all the neural network, all the neural networks serve the same thing. But then based on this biological mechanism, maybe we can actually design the neural network, or like we can design certain mechanism. They have different objective. And if they have different objective, then we can spatially design them and then try to optimize their accuracy, or like try to speed up their performance. They can actually do better because they don't need to do very general tasks. They can actually working on specific tasks. So then based on that, the reason they call them convolutional neural network is because they're having two parts of the job. One is called convolution. Okay, convolution means that you actually might find out some of the pattern exists in your image. Okay, so then that kind of pattern, you don't need to see the whole image. You can already understand that pattern, just like the ball I'm talking about. Okay, you don't need to see the whole image. You can see that pattern from very small region of them. And so then based on that, we do understand that if I consider in my image that my image doesn't need to be input to a bigger a whole graph, I can somehow understand that they do having some small pattern related to that. So in that case, I could partition my one image into small chunk of the image, right? If my job is try to learn the pattern, then for some reason, if there's a one image, I can partition them into 100 fragments. That implies I can actually enlarge in a virtual way, enlarge my training data set, because each image can be segmented and partitioned into 100 small image. Okay, so then if we understand that, and then we can also know that we don't need to see the entire image, and then we just recognize those patterns from a very small part. Okay, so that is the part about the convolution. So we don't need to see the image, and then we understand that there are different patterns across different places. And what we need to know is, if I want to understand what the meaning of this image, what I need to do is I try to combine the different patterns and interpret them in the end. So you can actually see, based on that, this convolution actually imply they have two different steps, right? One is try to segment them into the smaller chunk, and then one actually is talking about how to combine them. This happened to be one of the very important approaches always been mentioned in programming course or in data structure course. We call them divide and conquer. We have a big problem, and then we chunk them into the smaller problem. And since the problem getting smaller, it might be easier for us to know the answer. And then we know the answer from the smaller problem, and then we combine all the sub answer, become a bigger answer. So that is divide and conquer. Okay, so then if you understand about this one, then next one is, how did I segment my image? I can do some sampling, right? We already mentioned about sampling. So we actually can chunk my image into the smaller one. Once I actually having the image into the smaller one, so for example, in this image, I probably have 200 by 400, assume this is my dimension. Then if I need to take the whole image, I need to process 8,000 pixels right here. But then if I actually can chunk them to smaller segment, then like this segment, let me try to change my color into like right here, this very small segment. And this small segment actually probably just like 20 by 10. So as compared to originally 8,000 pixels, I just need to process them for 200. Try to process this 200 pixel. It'll be a lot faster when we try to working on that. And also because I only emphasize on those things, so then I will have less parameter. Okay, so that is the intuition behind the convolutional neural network. Okay, so then this is the overview about the CNN. Okay, so you can actually see the keyword of convolution being repeatedly mentioned in this framework. So here is a convolution, convolution, and convolution. And then between the convolution, you have certain thing called max pooling. Okay, we actually will tell you what's that about. And then you have this repeat, which means that they continue to repeat the convolution, max pooling, convolution, max pooling, convolution, max pooling. And then in the end, we try to flatten them. So when you heard about the terminology called flatten, which means that maybe they are just like two-dimensional data, just assume if they are two-dimensional data. Flattens mean that they become, I kind of make them to get thinner, so then will become one dimension. Originally it's like 2 dimension, this thick, and then after that I kind of flatten them into 1 dimension. So that is called flatten. And then afterward, they send the flattened information into a neural network. So CNN, you can imagine, is a very interesting design. If I say this one is a neural network, so it's more like data mining model. Okay, convolution, max pooling, convolution, max pooling. I actually can even imagine that why I need to flatten, because then they need to become the input into the neural network. And then afterward, the neural network will output and give me the label. So what the CNN did is adding something before a model. Okay, before we tell you that in the data mining, we do having the pre-processing, and then we having the method part, and then we have a evaluation. So you can actually find out the CNN kind of already adding part of the pre-processing step, but then make them merging them into the model and make that model interesting, because it's very genius design for having that kind of thing. So then why we actually try to having so many different layers? So in the convolution, we actually thinking that convolution is try to chunk them into the smaller part, because we believe that we will have the local pattern, and the local pattern usually are small in a very small region as compared to the whole image. And then after that, we do max pooling. Again, next one, we will tell you what is max pooling. Max pooling is like you actually try to do something, do some subsampling. And afterward, you kind of aggregate them. And the next one, try to having another pattern. So then let us try to show you an example. I did not generate this example by myself. And my previous TA actually tried to find some image. I think they create quite well, and then try to demonstrate them. So you actually can see, assume this one is original image. You can actually see they keep changing, but it's fine. Just see that this image is 5 by 5. And then you actually will find out that actually right here, we have a certain thing called convoluted feature. What does that mean? Okay, so did you see when the image keep changing, there's a one, looks like there's a smaller matrix. It's a 3 by 3 matrix. And what they did is they tried to do matrix multiplication. So they actually, you can imagine that they're having another one matrix, smaller matrix. In that matrix, they have certain value. And then they try to overlap. Actually go from traverse for a different region in this bigger one. And then afterward, after one traverse, and then they will try to extract one value out of it. Okay, so then afterward, what we did is, if you, because you actually can find out one thing is original image is 5 by 5. I go through some interesting process, and then afterward, this 5 by 5 and with this smaller matrix 3 by 3, in the end, I can get right here, we call them convoluted feature, get a smaller feature. Okay, so you might say, what does it mean? Then we actually were talking about that there, because then afterward, this is what we did for the convolution layer. So this is a matrix that we tried to talking about. Okay, but then right here, you can see this is smaller part of this matrix. And then you can imagine that I can having some of the, this one is a local pattern that we're talking about. So what is this local pattern? Because it's keep changing, we can actually, in assuming that this one, so for example, if you have the 3 by 3 matrix, and then we try to test a different shape to talking about what it is. So this matrix probably just inside this matrix only have the value of the 0 to 1. Why 0 to 1? Easier for us to calculate and then to show in that example. So assuming then right here, in this matrix, I actually mark this one as 1, assume, and mark this one as 1, and mark this one as 1. Rest of them, I leave them as a 0. So do you know what this pattern looks like? It looks like a line. So you can imagine I can have so many different patterns, okay? And then different pattern, they could be 3 by 3 pattern, 3 by 3 matrix. Some pattern are just a straight line. Some pattern actually are something like that. It's not a straight line. Probably is more similar to a circle. Okay, then you can see this kind of square circle. So then, and actually you can imagine I can create this very tiny small pattern right here. And so then I add this one, this kind of smaller one, we having a term, we call them filter. So this one is filter, F I L T E R. Okay, we call them filter. So we apply that filter, and then we go through my image, just like this image looks like they actually go through in a sliding window way. So when talking about sliding window, it's like we have a window, and then you usually we're moving the window, like I hope you can see me. So if that is a window right here, if I want to open my window, I try to draw them. So this is called sliding window approach. And this terminology being constantly using in computer science. So then we actually moving from 1 and then go for next one and go for next one. And then after that, we moving to the one in the button and the button. So then as you can see, that is how my filter move. Okay, so then after we go through then, different filter actually might be able to capture the pattern exists in this table. But when we try to go through this convolution layer, then we don't need to see from the whole image, right? Because each filter go through then is just like 3 by 3 part. And in the end, when we go this one, so what does that mean? So you probably say, oh, after I go through this one, I got a value called 4. Means that actually is more correlated to what I did. So we actually will get this convolution layer. And remember before, we say that next one, we have max pooling. So what does that mean? Okay, max pooling is we pick the one. So after that, we're having so many things. We pick the one from the batch where is the strongest signal. We can actually be able to help us to find it. And then afterward, we actually can reduce the number of the parameter. So after this one, and then you can say max pooling, then we find another filter. And then after that, we just say, okay, so I don't need to see this size anymore. We actually can go to a smaller size. Okay, by the way, this example are not directly related to all the image. We just try to utilize this illustration to show you what is called convolution, what is called max pooling. Okay, but if you want to know more about them, in the original paper, they have a lot of equation for you to go to. But then where the filter go, you can imagine they can directly come from random pick. So some of them might look like age, some of them will look like this one. And after we repeatedly go through the convolution, so here is another example, because you can have different pattern, right? So today, if you having a handwriting, and sometimes your handwriting might have different angle, like the 5 can go to this angle or that angle or that angle. And then in the pooling part, then we actually can try to show that, oh, maybe that one also, because pooling is trying to see which signal actually is strongest, which is stronger in my patch. And then they will be able to say, hey, okay, so then this 5, when I have in this direction, I can catch. And when I have in that direction, I can catch that too. So this filter with a different kind of filter will allow us to capture the pattern in different angle. Even I kind of rotate my image. So that is a good part about having a filter. And afterward, so you can actually see, let me go back to this one. So you can see convolution from a big one, and then I try different filter and that. And then after that, go to the max pooling one, and then we try to make my big matrix into the smaller size, okay? And then do the convolution and then into a smaller size. So in the end, when you repeatedly to go through many time, many process like that, then you won't having a huge data anymore. So then in the end, you can flatten them. So flatten is like you have different small patch after the convolution layer. And then we just, for example, you have 6A34, 6A34, and then I just make them to one dimension. So that is called flatten. So then after I have this output from the flatten way, it become a vector. And then after that, you just send them to a neural network. Okay, we just call them, we send them to a fully connected neural network. And the neural network in the end, they're going to learn something and then they will output. So then how we try to have the output from the neural network, they will tell you is a softmax. Softmax is like they try to get out which output would likely, what is the maximum output from this one, and then make that as an answer. So that is a softmax one. Again, that's everything I'm talking about are in a very simplified version. We just want you to know that the convolution actually try this type of the way. So you can imagine, because the convolution neural network, actually we're having so many different framework like that, right? So then based on the researcher study, the first convolution to the max pooling, and then you can imagine you can have many there. It looks like, when we try to get a clean water, we might also go through different filter, right? We might have actually say, oh, this one is based on, this one goes through the bigger rock. And then after that, we have the core right here in the middle. And then after that, we have the smaller filter and something like this. Okay, so you can imagine CNN, convolutional neural network, they have many there. Some people, actually researchers, think the early layer, and detect the some basic age and the stroke. Okay, and then after that, the middle layer detect some of the shape, or like a circle or eyes. It's more like a more aggregate shape. And the later one, so later layer probably will actually see a bigger object. Why is like that? Because you can imagine the early one probably try to process this very big one. And after mass pooling, my image getting smaller, right? So when I actually go to the next convolution layer, actually it's already smaller. Go to the next one, actually it's even smaller. So when I actually try to do the in the end before the flatten, so then I only have this part. So I actually can see the whole image in one time. So you actually can see the local part. You can also see the big one through the different layer of the image. So that is a very extraordinary design, I think. And okay, so then, but the thing is that this model actually has been proposed around 1989, but it did not get famous till 2000. Why people thinking now? People thinking the CNN is quite important. By the way, after transformer come out, then the importance of CNN maybe are not are decreased, not as important as that before. But then why the 2000 after 2000 thing actually were getting better? First is because we're starting to having so many different kind of the GPU and try to make the computation in faster. So make all the computation, the time actually getting smaller, and all the thing become faster, and then all the storage actually is getting less expensive. There are so many advances for our technology to make the thing are a little bit difficult to make them possible after 2000. Okay, and the second thing is as I actually just say before, that Li Feifei have this ImageNet, and then when they have the first ImageNet competition, and then the winner are called I think it's called AlexNet. Okay, AlexNet, and this AlexNet actually have a bigger, so many stack of the convolution layer and thing like that, so many different things. And then at around that time, it is the first winner. So it makes people to feel amazed, like, oh, how come they can be so good, and the performance are also wonderful. But then actually, if you try to traverse the ImageNet, the results for the first year, second year, third year, and fourth year, and continue on, you will find out that even though we say AlexNet is very good, but then the second year, the winner is a lot better than AlexNet. But because AlexNet is the first winner in the ImageNet, so everyone just remember that, and everyone want to know how they try to working with it. And then they utilize convolutional neural network, so make people to feel like, oh, maybe we can also do better than that. So then the remaining part of this people try to working with the CNN, they just try to stack all the different layer, many hidden layer, and many convolution layer, and the max pooling layer, to many things. That is a quite interesting part. So in the end, you will see people try to call them deep learning, deep neural network, or deep learning. Why? Because they have so many layer. Okay, so then I think we're talking about that story. We give you some concept. Next one, it will be you to talking about what limitation can the CNN try to address. So you can pause this video a little bit, and then we will come back. Okay, so let's go back to check the our quiz, and then because this year we do not have the time to check your result, so let me try to go through each option one by one. So which limitation of the neural network can convolution neural network try to address? And the first one, high computation cost of the training for the large-scale network. CNN did not really reduce it. With all the convolution, max pooling, convolution, and max pooling, actually it increased many process. So then, in the end, it could be a lot heavier than before. So second, poor ability to capture spatial locality in image. This one is correct, because with all the filter, and remember what we're talking about the filter, and then we can actually understand how the spatial rotation is, and with also the max pooling, because we try to merging them, so it actually can capture, it can really help us to capture a better way for the spatial locality. Okay. So the third one, efficient feature learning without manual engineering. This one is also correct, because all the filter actually are not designed by human being. It can be randomly generated, and then we just utilize different filter, and then we will be able to test which filter actually is more effective, and then after the convolution, if the not that effective one can be fade out, so then it could help for that one. Okay, lack of the transparency in the model interpretability. This one is wrong, because it still maintains a black box. Okay, so the last option, excessive number of the parameter in fully connected network for image input. This one is right. Okay, because as we actually showed this one, the example to you before, that the our image, no, I don't. So you you originally having this big of the image, and then through the different convolution, actually just getting smaller and smaller. So it could help us to reduce the number of the parameter. Okay, so then the next set of the question. So which limitation of the genetic neural network are lessened? So what kind of problem and can be lessened by the CNN? The first one, large input dimensionality in image. So can that solve? Yes, because actually by utilizing max pooling and wish the convolution, in the end, it can really help to deal with this very large input. So then that can help. Okay, the second one, presence of the BIOS in training presence of the BIOS in training data. That is no, because then if our data are BIOS, and then CNN design did not really design to alleviate that problem. And maybe because the filter design, you might make the BIOS, because then all the smaller sample thing, and if you have so many different parts, and so maybe in the end, it probably would even endanger for the CNN. So then the BIOS, the data BIOS, supposedly should be somehow reduced beforehand. Okay, the next one, sensitivity to the small shift in input. Yes, that could be solved, because this pooling layer actually is try to be pooling actually is more like aggregate. So then you need to know aggregate usually make our result more robust. So this pooling layer actually make the CNN more robust to the small. If they have some shifting translation, actually that is a lot better. Okay, so the fourth one, difficulty in automatic extracting hierarchy feature. And then this one is also right, because with so many different layers, remember what we say? So then the beginning layer actually is better for like age and that. So you could actually see that kind of hierarchy way. So then it somehow can alleviate certain thing. And the last part, saying the large training data requirement. I personally believe that CNN can also help with it. And why? And because then you can actually see the fully connected layer. If we do not have CNN, you really need a lot of large data sample to make that work. But CNN reduce the need of the parameter. And then so then because the parameter being reduced, so the size of the training data doesn't need to be as big as before. Okay, so but then again, CNN still be benefit a lot from the large data set. It's just not that demanding as the original design. Then the last one, question 3. Question 3 say which challenge is applied in the neural network to vision text are addressed by CNN. The first one, inability to generalize across position in image. Just like we say, then the original neural network, if we did not actually do this convolution, then you might, for example, if there's a cat on the upper corner, and then it might having the difficulty to understand if there's another image, the cat is in the bottom right. So then if the position just change, and the fully connected network probably will difficulty to know that it's a cat. Okay, but CNN with all the convolution and pooling, and so then they won't having the problem to recognize it. So this one is correct. And the second one, manually designed for image feature like age and texture. And that could be correct too, because CNN all the filter are randomly select. So they don't need some expert to manually design what kind of feature is more important. So this is right. The third one, difficulty in capture long range of dependency in sequence. Okay, CNN did not really talking about long range dependency problem. Okay, if you want to know this one, wait till that we having the text mining when we go to the transformer. That is the part they try to working with. Okay, but CNN did not really try to working with that. So if you do not understand what I'm talking about, it's totally fine because it is you haven't learned what is called long-range dependency yet. But then the last one, lack of the fairness in BIOS data set. CN also, as we say in the previous one, it did not really design to remove the bias problem. Okay, so then I think that are the topic of what we want to talking about. And those few different topics, I think, are the one I consider quite important when we're talking about the classifier. You might actually know they're having a lot more classifier that we did not talking about. So then try to give you certain reminder. This is a great paper, and they having some AI expert try to share with us last year. Say that if you want to know more about the machine learning, it would be nice for you to check this paper. In this paper, they give a certain reminder. Okay, so I want to utilize this reminder to remind you as well. First, what is learning? We heard about learning a lot. Learning usually means representation. And then you always the evaluation. And then after that, you improve it. So optimization. So the learning is mean representation plus evaluation plus optimization. And then as we say in the very beginning, no matter how fancy your algorithm is, feature engineering still is the key point, key concept. So then try to utilize a lot more model. And then the best you will find out when we try to go for the competition. If you only rely on one model, then you probably can only perform as mediocre, average. Okay, so why? Because the best model from all the competition are usually ensemble method. So which means that you try different method and then try to compose them. So there are many more model. If you see model and try to understand that, you don't need to know all the detail. Just need to know, probably what is the basic concept behind them. And if our model actually are our problem are representable, and because you know representable means that you have representation, but then we don't know can they be really learnable, because maybe evaluation part you have the problem or optimization part you might have the problem. And one very important thing, correlation doesn't usually reply to causation. So then which means that if you see some correlation, it doesn't mean that it's cause. Okay, so we probably will talk more when we go to the association rule. But if you're interested in that, you can check this paper. I think they have a quite good reminder. They do having a lot more classification method. I have no intention to go through them, but then do having some of the concepts that are frequently being mentioned. And one of the things being utilized in recommendation system, remember the Netflix story and thing, actually people talking about K nearest neighbor. If you took the recommendation system, actually you might actually can have like 1 hour, 2 hours, 3 hours of the what kind of the recommendation system usually try to design, but we don't really have that time. So I just want to give you very naive approaches. And naive approaches for K nearest neighbor is called naive approaches for the recommendation system is called K nearest neighbor. What does it mean by K nearest neighbor? So just imagine if I actually have every person can be represented as a vector or as a point. So then right here, you can see from this Netflix system, and you have a matrix, a huge matrix, and then you have so many user in your row. So all the row represent the user, and your column represent the number of the product, the different product. Okay, the different book, different DVD, different kind of product thing right there. So your column actually are all the product actually can be purchased from the Amazon or from the Netflix, depends on which one is your recommendation system domain. Okay, and why? So then your role actually right here are the user. So each one of them, in the end, I can convert them to a vector. And then I can also try to plot them in my multi-dimensional space. So assume this one is my multi-dimensional space. I find a user. Right here is user called XQ. Okay, so in my space, I can find some user. Actually, I call them my neighbor, my nearest neighbor, because they are closer as compared to any other element. So if I say k nearest neighbor, for example, in this case, my k probably will be equal to 1, 2, 3, 4, 5. So 5, my k equal to 5. So then I actually, in this circle, I got 5 nearest neighbor. What I mean is like their behavior are quite similar than I am. Okay, so then after it, so by the way, then right here we say in terms of Euclidean distance, because based on this example, if you say, Professor, does that has to be Euclidean distance? Not necessary. You can utilize Minkowski distance, Manhattan distance, whatever distance or cosine theta based on what you did. I just say based on this example, we utilize Euclidean distance to demonstrate that. Okay, and then afterward, then you actually will get your neighbor. So then, for example, right here, why we still call the classifier or dynamo thing, sometimes we're talking about the utilize k n my method. So for example, 1, 2, 3, 4, 5 right here. So you can imagine this 5 element belong to this XQ class. So they can be considered as like classification as well. I want to know which element belong to SQ class. They are similar. So you can utilize K nearest neighbor to find those 5 elements. And why is that important? Because in association rule, they have another hypothesis. So we actually, in English, they have the term called flock of birds, right? Means that the people surrounding you, if you are similar, and then you will have very similar behavior. So today, just imagine right here, let me try to utilize some example right here. Assume this point actually in the end can be convert back to this vector again. Okay, so then this field back element actually is closer as compared to other element. So then, as I say, the column could be the product. Okay, so it can be the product. Okay, so this is SQ. SQ, actually, let me try to use a different color right here. SQ like this product, like this product, like this, and that, like this one. Okay, so then right here, I have his neighbor. So assume this neighbor called A. A also like this item. A actually have very similar pattern, just like SQ. So this pattern, and this pattern. So see, many pattern. But then there's certain element SQ did not, the A did not have. Like this one, they did not have. But A actually having 2 more element that SQ did not express. It like, okay, so for example, you're having something like that. And then you probably also having another user. Let me try to find different things. So this is called B. Okay, B actually, this one are similar to the A and like that. Okay, so that is how B's it's quite similar because you will find out certain items actually are identical, right? But then A and B having some extra element that SQ did not have or B did not have. So in the recommendation system, what we did is we will recommend, slightly different. This item to SQ and B. I can also recommend this item to A. And then you can actually see SQ actually having this part, so I can recommend this item to A. So that is how the recommendation thing look like, because you are look like. So your friend, what your friend like, you might likely to like it. Okay, so that is a k-nearest neighbor. I hope that is clear. And so then in the k-nearest algorithm, they have so many different ways that we can try to working on. And one very important thing people usually try to pay attention is like, how do I do the weighted? Maybe certain feature are more important. Yes, you can also have in the weight. Okay. And then do we suffer the curse of dimensionality? Yes, it did. So then you actually will also find out in the Netflix winner before, the people actually were talking about next concept called SVD a lot, because they try to combine the KNN with SVD together. Okay, and not SVD. Okay, so SVD and SVM, so they have so many different SV. Okay, so then next one I'm going to talking about is SVN. By the way, you can also have SVD thing being talking about. So when actually they have a lot of metrics, and then you can see so many different ways for them to somehow reduce the size. SVN actually is another classification method. They try to do one thing is try to find some new dimension. Okay, what does that mean? Okay, you try to find a hyperplane. So why we call them hyperplane is because they are some plane, but they are not two-dimensional. So they are in multiple dimensional space. So that is why we call them hyperplane. And then we try to find a hyperplane, just like our PCA also try to find some vectors, find some projection. SVN try to find this hyperplane, and this hyperplane, and then the philosophy. By the way, I do not want to talk about equation. If you want to, you can go to check for some other video for SVN. So what they did is they try to find out, assume I have this class, I have another class, and then right here, I would like to find a plane can give me some margin. So for example, the same data set, but then I probably will find out that right here, this margin from this set to another set actually is larger. So then I would prefer to utilize larger margins hyperplane. So that is the concept. If you don't know what's that, it's fine, because it's just so many different methods that you can choose in the one you prefer to look at. And so we can utilize different support vector, try to find out this kind of margin. Okay, so I think I basically to go over some basic machine learning method. Okay, the next one I would like to go over the summary about them. So what we did in the last week and this week, we try to go for so many different classification tool. Okay, and in classification, one thing you need to know is we call them supervised learning, and then we require training data and the testing data. And inside your data set, you require one attribute. We call them class attribute that will give us the answer. And then try to be aware that you might have in the overfitting problem. And we have so many different methods. So in our session, we go through a longer detail for decision tree, random forest, naive Bayesian classifier, and neural network, and the convolutional neural network. And they do have a lot more, like the KNN, we try to mention, and the SVN, and so many other things. And then here is the overview for decision tree. First, in order to having the decision tree, decision-like tree, all the attribute in the end will be converting into categorical way. And we utilize greedy approaches to finding our tree. And then we utilize so many different measurements and to calculate the information gain, such as entropy and Gini and different things to calculate our information gain. and it's quite inexpensive as compared to other methods, and easy to explain, interpret. And then when we have a small size of the tree, it will be a lot easier for us to talking about what is that about. Random forest is like a variation from the decision tree. It's more popular as compared to decision tree right now, and especially when my training sample are small. Okay, and then I do not having quite many feature, and we usually utilize random forest will give us very good result, and also because it's decision tree like, so all the way thing right there can help us to interpret, to explain about them. And what they did is they will try to create some sample, bootstrap sample. We utilize backing way to get our training data, construct so many different trees, and then afterward they try to do the majority vote. So it performed very well for a small data set. When I say small, it's like 1,000 or like 10,000, very, very small. But the Naïve Bayes is also a very good baseline. It based on the probability to solving the classification problem. And then it's quite easy to implement. They also usually have the good result. But then if you have too many dependency among your variable, it probably will not perform well. Neural network will spend so much time on talking about it. It actually gives you a lot of neuron, and then between the neuron, you will have the connection, the weight. And then the neural network requires a very large set of the training data. And then you also require a huge, significant need for having all the computation resources. And then all the model look like a black box. So if you are going to explain it, it become difficult. Convolutional neural network is kind of variation of the neural network, but they try to construct it for grid-like data. In other words, they could be image. If your data can be converted into grid-like, it can also utilize CNN. And they have the convolutional layer and try to utilize different small filter to detect the feature. And then also having the pooling layer, they try to reduce the size. And it will be quite effective if you want to reduce the parameter. And one thing that we mentioned in the kind of in middle of the classification one is we give you different way to do the evaluation. And the evaluation are quite important. So then we give, the first thing we try to give you is the accuracy, but then we try to say if the class size are different, so accuracy probably will be misleading. So then in order to having more sensitive, cost sensitive mean like if the class size are a bit different, if I want to emphasize on that, so I can utilize precision, recall, and F major. So usually we can call them F1 score. And then we also utilize tests of significance to compare different models to see are they good or not. If we find out the model's confidence interval overlap, which means that they are not significant. But if we find out they did not overlap, so we can clearly say which model is better than another model. Okay, so this one is a final reminder. You might say, oh, Professor, I already did read this slide before. Yes, you are. But then you can actually find out classification. We're talking thing right here. Okay, we're also talking about evaluation is right here. Why is that important? Okay, a lot of time, I think some of my some students when they try to do their research or then when they try to do the work, and then they usually thinking about, I don't know does this method work or not. I don't know if that is a perfect solution. Okay, but then right here, the reason we tell you the evaluation is because you can move, you can take your action, but then don't expect your action will give you an optimal solution. But it is fine because you try to utilize evaluation to work with that and then come back. Okay, and I also, when I went to the different speech, sometimes I tell the student, please don't only emphasize on the outcome. Pay attention to the middle one. Pay attention to your journey. And the student will tell me, but Professor, how do I not to pay attention to the outcome? Okay, so then how do I pay attention more to the journey? Because no matter how I try, I still get my outcome. Yes, it is right. So no matter how you do, and in the end of semester, you will get a grade. So you can imagine the grade look like this evaluation. Your life did not end just because you got a grade, right? You test that evaluation as a guideline, knowing what need to improve. So we don't end right here. We come back. You test that guideline to know how to improve. Or if that's not okay, come back right here to do everything again. So it's a recursive way when we try to do the data mining. Okay, and I think that is also a recursive way when we try to thinking about our life. Okay, we have different way to evaluate. For one evaluation, if that's fail, failure, it is fine. It doesn't mean that our life just down, doom. No, just come back and then change a different method and do that again. And so don't take anything too serious, like, I only have one chance. No, you have many, many chances. And I hope you actually encounter, have that experience and working with your lab one. You might find out, a lot of students already tell me, that lab one are so difficult. Yes, we know. We actually need to train you with some challenging thing to actually make sure all the information that we're talking about so far. And with that practice, you might understand more. Okay. So then I hope after that, this is a quiz. And then I hope you, when you actually listen or try to go through this classification, it's not just about the technique. You'll find all the approaches. You can, for example, CNN actually is being inspired from our understanding from the biological mechanism. So then I think when we study the data mining, it could probably become some inspiration for our life philosophy. Okay, so working on that, there's no standard answer right here. It's just for you to do the brainstorming. And then that will be it for today's session. And here are our 1 minute reflection for today. Thank you very much. I will see you a few weeks later. See you in October 13th. Okay, bye-bye.